Okay, now let us write a simple program to blink an LED using both Keel as well as the Proteus software. So let me write I have already created the project and if you see, the target is 89 C51 and the frequency is 11.0592 megahertz. So let me write the program quickly. Start start. I will if I have to blink the LED, then I need only one terminal. So let me assume that I will use P2.0 to generate a square wave that will be connected to the LED. Okay, so I'll say CPL P2.0. okay, then I'll call delay LCALL DELAY, then jump start. So basically I am complementing and then calling a delay, and then I'm starting, I'm going back, looping over the, not starting, looping over the DELAY. Now I have to implement the delay routine. So I'll say move R4, I'll use R4 comma hash 20 h then I'll use R4 and R5. So then I say for loop move R5 comma hash 0 ffh. okay, then I loop djnz R5 comma I loop. okay, then I say djnz R4 comma O loop, and then RET and end. Okay, so this will introduce a delay 32 into 255 number of times. So that's all. Okay, so basically it is decrementing R5 and just introducing some clock cycles, machine cycle delay. Okay, so nothing great about this program. Let me compile this. Okay, so I have no error, so it's created a hex file called as LED flash. Now let me go to the Proteus software. So I have to, now I have the microcontroller, that is AT89 C51. So P2.0 will be the point where I will be connecting my LED. So I say place components and then I'll say LED red. So I'll place it here, then place component. I'll also have to connect it through a resistor because the current through the LED cannot exceed approximately 20 milliamperes. So place component and the resistor. Where is the resistor? Okay, so I will place it here. Okay, I will call it as, I'll make it 330 ohms. Okay, and then I will rotate this right by clockwise and then align it under the LED. Then I'll introduce a terminal called as ground terminal. Ground terminal. So I have placed it. Somehow the right click is clicked sometimes. Okay, so I have placed the ground terminal. Now I'll connect the ground terminal through the resistor. I'll connect the resistor to the LED. Then I'll connect P2.0 to LED. The connection is through, and then I will use my LED flash hexadecimal. Then I have burnt it. So my program is loaded and my circuit is also finalized. Now let me run this. When I run this, what I should see is the LED blinking. So let me see whether that happens. I'm running. Okay, so my LED is blinking at a very fast rate. So I'll slow it down by going back to keel, and instead of 20 I will introduce a delay of 0 f0. So this will give a bigger delay. So let me compile this and let me run this now. Okay, so now you can see that my LED blinking has slowed down. So if you want an exact delay of 1 second or 2 seconds, then it's better to use timer. So right now I have created an arbitrary delay. Okay, so that is about the simple LED program. Let us revisit the stepper motor program that we earlier discussed. This particular program drives the stepper motor using wave sequence. So we have the sequence of 8, 4, 2, 1 when we rotate it right. So that is going to be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0 and 0, 0, 0, 1. Okay. So having talked about this sequence, so what we did earlier was we ran this program and we saw the waveform output using logic analyzer. Now we are going to take this program a bit further, and we are going to simulate the circuit connections along with the drivers and the stepper motor. So what we are going to do is we are going to use a software called as Proteus. Okay, so here we will you have a microcontroller, then we are going to interface a driver with the microcontroller, and then we are going to connect a stepper motor further. Okay, in order to connect a driver, let us select one driver. Let us see the number. Okay, we are going to select ULN 2003A. Now what this particular driver is, it is a high current Darlington transistor array. So if I see the circuit, so it takes an input at 1A, 1B, 2B, 3B, 4B, 5B and 6B and 7B and provides the output from 1C to 7C. Okay, and if you see, the output is negative. Okay, so the output 1C, 2C, 3C and 4C are connected to the stepper motor, and 1B, 2B and 3B and 4B is connected to the microcontroller. So we need only 4 pins because the stepper motor contains only 4 phases. Okay, so let us go to the Proteus and let me insert ULN 2003A. Okay, so I'll go to the component and then insert ULN 2003A. Okay, and then I'm going to insert even the stepper motor. So components, and I'll say stepper motor. Okay, good. So let me move this. Okay, good. And here we have 6 terminals, out of which 4 terminals are the phase terminals, and 2 terminals that are in the center on the left hand side and right hand side, they are the common terminals. So I will connect the common terminal to VCC. So I'll say power terminal. Okay, so here, and then I'm going to connect the center terminal to the common terminal. Okay, done. And this common terminal also I'm going to connect here. So let me zoom in. Okay, so this P2.0 I'll connect to 1B, P2.1 I'll connect to 2B, P2.3 I'll connect to 3B, P2.4 I'll connect to P2.3 I'll connect to 4B. Now I will connect 1.C to one phase of the stepper motor, 2.C to the next phase of the stepper motor. Okay, so let me, okay, then 3 dot C I will connect to the next phase of the stepper motor, and 4 dot C the other last phase of the stepper motor. Okay, at the same time what I'm going to do is I'm going to place a digital oscilloscope, okay, so that I can see the phase A, phase B, phase D, phase C waveform. So phase A I'm going to connect to A terminal. I think let me not do this. I will connect the last one so that the number of crisscross are minimized. D I will connect to phase D, let me call it as phase D, phase C, then phase B and phase A. Okay, good. So I'm done with the connections. So let me see the circuit again. Okay, so I'll zoom out. So the microcontroller is having, now what is the microcontroller? Let us see the zoom out and see what is the microcontroller number that I have. It is 8089C51. okay, and it is connected to a crystal oscillator that is running at 11.0592 megahertz, and then it is connected to the driver. Okay, and from the driver it is connected to the servo stepper motor, and then it's also connected to the phases are also connected to the CRO. Okay, so with that let me go back to the normal zoom, and I'll also, okay, so now I'll burn the stepper motor program to this microcontroller module. Okay, and I will run the program. Okay, so it has started showing me the waveform in phase A, phase B, phase C. Now if you see simultaneously, okay, so I think let me stop this and let me now run it again. Okay, so the waveforms are here, and if you see the stepper motor is running in a clockwise direction. So I'll pause for a minute. Okay, so if you see the sequence, it is 1 1 1 0 0 1 1 1 1 0 1 1 1 1 0 1, then it comes again 1 1 1 0. So that corresponds to 0 7. So this is 7 0 7, and then it is 1 0 1 1. So that is 0B. Then it is 1 1 0 1, that is 0D. Then 1 1 1 0, that is 0E. So that is the sequence that we have, and if you run it, the stepper motor is rotating in a clockwise direction. Okay, let me stop this and let me go back to the key and change the sequence. So instead of rotate right, let me say rotate left. Okay, rotate left, and then let me compile this. No error. So I'll go back to the proteus. Now that let me reselect the stepper.hex. Okay, and now that I change the sequence, I should see the stepper motor rotating in a counterclockwise direction. Let me see whether it happens. Yeah, the stepper motor now rotates in a counterclockwise direction. We'll go to the next example of demonstrating DAC interface. We have earlier seen the program of the DAC. So let me open the program in the keel. So we are in the keel, open the project, and we had the DAC project. Okay, so let us see this program. Okay, this particular program that we have is generating the sample one. So let me remove this file and attack the sinusoidal generation program. So I'll go here and add existing file, and we had the ramp. So I think I wrote the program in this. Okay, yeah. Actually the file name is ramp, unfortunately. Okay, so I have written the sinusoidal wave generation in that particular program. Okay, so this program which we had seen earlier was generating a sinusoidal wave, and there are 12 samples, and we have seen the output of this using logic analyzer. So I'll compile this particular project, and this creates a hex file called as DAC. So this program generates a sinusoidal wave with 12 samples. Okay, now we'll go back to the keel. We'll go back to the proteus. Let us see this. This is a microcontroller, and this is a digital to analog converter. So let me zoom in. So I have used DAC 0808. Okay, so the microcontroller port 2 gives an output, and that is connected to the input of the DAC. Okay, and the reference voltage is 5 volts and the resistor is 2.5k. So the reference current is going to be 5 divided by 2.5k, that is going to be 2 milliamperes. So the maximum output current is going to be equal to 2 milliamperes. Okay, so how do we do that? How do we rig up the circuit? I'm not going to go into the details of this. So the same procedure of whatever we demonstrated in stepper motor, the same procedure needs to be followed for adding component. Let me add DAC and show it to you. So you say right click on the worksheet, place component, and then you say DAC 08 and you drag and drop it, so it will drag the DAC. Okay, so I'm not going to do that. Okay, but if you see here, very peculiar, the output of the microcontroller P2.0 is the LSB and P2.7 is the MSB. So I have named it as D0 to D7, and if you see the DAC 0808, 5 is the MSB and 12 is the LSB. So what I have done is have used terminals. So let me demonstrate how to use terminals in Proteus. Okay, so I'll remove one terminal, and then the same procedures can be followed by anyone to set up a terminal. So since the port 2 provides an output, I have defined output terminal at port 2, and since DAC needs to be connected to the input, I have to define input terminals towards the DAC. Okay, so right click and say place and then say terminal. You can see there is an output terminal, and again right click, place terminals, there is an input terminal. Okay, so align the input terminals and output terminals in the respective locations as shown in the figure. So either you can do the drag object, so you can drag the object. Now it has to be labeled. So if this has to be connected, pin number 21 has to be of the microcontroller has to be connected to the pin number 12 of DAC, so then it has to be labeled. So I will double click and say that edit properties at the terminal, and then I will name it as D0. Okay, so basically now this has become a D0 terminal. So this is an output terminal named as D0, and that will be mapped or connected to the input terminal D0 of DAC. Similarly, the output terminal of P2.7 should be connected to pin 5 of DAC. So I have created a input terminal. I have to name it as D7. Okay, D7, and then I will connect the wires, the ends of the input terminal as well as the DAC. Okay, now the connections are fine. So why I have done this terminal definition is to avoid the lot of crisscrossing of the wires here. Okay, and if you see, the output is connected to CRO, so I am using only one channel of the CRO, and since Iout provides the output current, I need to have a output resistor. This resistor converts the output current to an voltage. So if the reference voltage is 5 divided by 2.5k, that is 2 milliamperes. If the reference voltage is 2 milliamperes, the maximum current flowing through flowing out of pin number 4 is 2 milliamperes. So the maximum output that is generated is 2 into 2.5k. So that is going to be equal to 5 volts. Okay, so with that, let us start the simulation. Okay, so this generates 12 samples sine wave. So let us see whether we are getting that. Okay, so we can see in this output CRO output that it is generating a 12 sample sine wave. So this was what I was expecting. So the program is working fine. Let us talk about interfacing with the 7-segment display. So before we proceed, I'm going to open the page that gives me the mapping of 7-segment display. Now if you see the 7-segment display, the 7 segments in that particular modules are arranged as A, B, C, D, E, F, G. So based on which LEDs are on and which LEDs are off, the digits 0 to 9 will get displayed. Say for example, if out of this 7 LEDs, if G is off, then you have a numeric 0, and if only B and C are on, then you have a numeric 1. So if all are on, so then you have a numeric 8. So this table gives me the the mapping of all the numerics with respect to which LEDs will be on in the 7 segments. Say for example, if you want to achieve the 0 to be displayed, and if it is common anode, then this has to be 1, and whatever is marked as cross should be 0. Let me repeat it. If it is a common anode 7-segment display, if you want to display 0, then G has to be 1 and the rest of the digits has to be 0. Okay, so it will be 0 0 0 0 0 0 1. So it is 0x 0 1. And if you want to display 1, then only B and C should be 0 and the rest of the things have to be 1. So it will be 4F. Okay, so if I go to Keel, I have created a numbers, I have created a data to display 0, 1 and 2 and 3, so on and so forth. Let me go back to Keel. So this corresponds to 0, digit 0, this corresponds to digit 1, this corresponds to digit 2, 3, 4, 5, 6, 7 and 8. If you see 8, all the LEDs has to be glowing. So since it is a common anode, so we have this particular, all the terminals at the lower potential, so that ends up in glowing all the segments in the 7-segment display. And this is 9. Okay, now I have put this, calculated this and put this in Keel. I also written a delay routine so that I can save time in explaining these things. Okay, so let me write the program. Start start. So I have, now my objective is to display in the 7-segment 0 and 1 2, like basically it's I want to display a counter in the 7 segment display. So how to do that? So first there are 9 digits. So there are 0 to 9 is 10 digits. So I say move R7 comma 0 AH. Okay. So then I need to point my DPTR to the data where I keep this I keep the data, that is S data. I need to point my DPTR to S data, because S data will contain all the digits correspond to 7 segment display. Okay, so I say move DPTR comma hash S data. Okay, and then I will say loop LOOP. First I need to get the first data, so I say move A comma move C. I have to use index addressing mode because these data are in the program space. Move C A comma at the rate of A plus DPTR. Okay. After that I will put the value of this input to move P2 comma A. Then I will reset A. This is because this is an index addressing mode. I need to have the offset clear, so I need to get the next data. So I say INC DPTR. Okay. Once I have done that, I will say delay. I'll call delay DELAY. So let me introduce very high delay in the program so that I can see the counter being operational in the in my 7 segment delay. And once I did that, once I have displayed 0, then I will have some delay. Then after that I will display 1. So the 1 is in the next location, so I have to keep on fetching the next data and as and when I display 0, the next one will be 1 and next one will be 2, so on and so forth. I'll say DJNZ R7 comma loop. Once it has displayed from 0 to 9, then it has to go back and display 0 to 9 again. So I'll say a jump start. Okay, so that is the program that I have. So let me compile this and see if there is any error. Build target. Okay, missing end statement. Let me write an end statement toward the end. And okay, so I have the program. Okay, so it has generated a file. Okay, let me recreate the project so that the naming conventions are all appropriate. I'll rename this file project, save project as file new project. Let me cancel because I have written the source code to a LED blink project, so it doesn't look good. So let me redo this. Okay, paste. Okay, so let me redo the project. New, so I'll say no, yes. Okay, so yes. Okay, so I'll create a new project called as 7 segments, 7 CGMENT. Okay, so 7 segment, 7 CGMENT. So let's create it. So it is 80, 89, C51. Okay, this is the microcontroller that we are generating the project for. Let us change the clock frequency to 11.7.0592 megahertz, and let us create a hex file, and let us add a new assembly file for this by name 7 segment 7 SEGMENT. Okay, and let me paste all my assembly logic to that. Okay, we are done. So let us build this. Okay, now this looks better. So it has created a 7 segment hex. Okay, so we'll go to Proteus, and I have already rigged up the circuit. This is the microcontroller. Okay, and this is my 7 segment display. This is A, B, C, D, E, F, G. Okay, so this is a common anode. This is connected to plus 5 volts, and these resistors, they are the current limiting resistor. They are all configured to 330 ohms. Okay, so let me write this program to the 8051 module. Okay, and once I've done that, let me run this. Okay, so if you see the 7 segment display, it displays from 0 to 9. Okay, so there is some small error. So let me go back to my program and see what is the error, because I expect it to run recursively. Unfortunately, it is not happening. It is R7 0AH DJNZ R7 loop. So this is fine. Increment DPTR L-call delay DJNZ loop and AJump start. Okay, so that looks fine. Anything? No. Okay, that looks fine. So 0A hash 0A. Okay, so let us get started again. Okay, so let me build this. Okay, so and let me go to the Proteus and let me rerun it. So let me see, 0 1 2 3 4 5 6 7 8 9 0 1 2. Okay, so if you see now, the 7 segment display is working as a counter. So it is displaying numerics from 0 to 7, and it is doing that indefinitely. So let us go back to our key program again. So if you see, I have 10 numbers to be displayed. Where are the numbers defined? Numbers are defined here. And how did I define the number? 0 correspond to 01H. How did I do that? Since it is a common anode, this should be off. So this should be 1. The rest of the things should be 0. So 0 corresponds to 01H. And if it is 1, then only 2 LEDs should glow, that is B and C. B and C should glow. So then this should be 0 0. This should be 1 0 0 1 1 1 1. So it is 4F. Okay, so let us go back to our key. So 1 corresponds to 4F. So then the rest of the things follows. Okay, so we are calling this one by one. So we are pointing this to the data corresponding to 0 initially. Then we are getting the data corresponding to 0, and then we are putting it to port. Then we are clearing, because this is a index addressing mode. Then we are incrementing DPTR. We are calling the delay 4 times. Then we are going back here. It will fetch now, since the DPTR is incremented. Now it will fetch 1, and then it will display 1. Then again it will keep on executing this loop till R7 is 0. Once R7 becomes 0, it will jump back to the start program and display 0 to 9 again recursively. Okay, that is about the 7 segment program. Okay, let us talk about now the head bridge circuit and control of DC motor using a head bridge circuit. So here in this diagram we have the microcontroller 8089C51. Then we have power transistors. This is not a power transistor, it's a high current transistor, 2N2222. We have arranged 4 2N2222 in this fashion. Let me go and see the specification of 2N2222. Okay, so the specification of the transistors are always available in the internet, so you can download that. So the rating of this is given here. So VCEO, that is 50 volts, VCB is 75, and emitter to base is 6, and the maximum current IC is going to be 800 milliamperes. So I'm assuming that I'm planning to run a very small DC motor, not a sophisticated or high power DC motor. Coming back, so the 4 transistor 2N2222 are in the legs of the H bridge. Okay, so this is they resemble the H symbol, so that's the reason it's called as a H bridge. Now Q1 and Q2, Q3 and Q4, the base are connected to port 2.0 through the resistors. Okay, and the intersections of Q1 and Q2 forms one terminal of motor, and Q3 and Q4, wherever they intersect, they form another terminal of the motor. Now let us assume that Q1 and Q4 are on and Q2 and Q3 are off. When Q1 and Q4 are on, at that time the left hand side of the motor is positive and the right hand side of the motor is grounded. So at that time the motor will continue to rotate in one direction. Okay, now if Q1 and Q4 are off and Q3 and Q2 are on, at that time right hand side of the motor will be positive and left hand side of the motor will be grounded. So the motor will rotate in a other direction. Okay, so now if Q1 and Q2 are on, so then what happens? So Q1 and Q2 are on, then it is equivalent to a short circuit of a transistor. So this is not a valid switching sequence. Okay, and similarly if Q3 and Q4 are on, again it is a short circuit, so it is not a valid switching sequence. So the valid switching sequence to make the motor run is either Q1 and Q4 being on or Q2 and Q3 being on. When Q1 and Q4 is on, it will rotate in one direction. When Q2 and Q3 is on, it will rotate in another direction. So we have to exercise utmost caution that we never have a sequence having Q1 and Q2 being on. So now with this, let us see how to run a motor in one direction. So if you see, Q1 is mapped to P2.0, the LSB of P2. Q2 is mapped to the next bit. Q3 is mapped to the fourth bit, and Q4 is mapped to the third bit. Okay, so P2.0 is going to will enable Q1. P2.1 will enable Q2. P2.2 will enable Q4, and P2.3 will enable Q3. Now let us say that we want to switch on Q1 and Q4 only. At that time P2.0 should be high as well as P2.2 should be high. If we want the motor to rotate in one direction, then P2.0 should be high as well as P2.2 should be high. So let's go. So this is nothing but 0, 5. It is 0, 0, 0, 0, 0, 1, 0, 1, which is nothing but 0, 5. Okay. So let me go to the key. So we say that move A, comma #05. Then we move 05 to P2, and then we keep on doing this. Okay. So this program, this is a very simple program to make the motor to rotate in one direction. Okay. So let me compile this and let me go to the proteus and let me load this. In order to load this, I need to know the hex name. So the hex name, as in the key, is nothing but H bridge. Okay. So let me load the hex bridge.hex. Okay, so hex bridge.hex. So it is hex bridge.hex. Okay, so I have loaded the hex bridge.hex to the microcontroller. Now let me run this and let me see what happens. Okay, so we have duplicate references, so there is a problem in the circuit. Let me go back. Okay, all the resistors are named as R1, so that is creating a problem. So let me change the value name of the second register to R2, okay, and third register to R3, and next register to R4. Okay, fine, and let me save this. Okay, and let me now run this. Hopefully there should not be any error. Okay, so if I see if I see the signals R1, I'm getting a signal to R1, I'm getting a signal here, and I'm getting a signal here. So that means Q1 and Q4 are on, and the rest of the transistor Q2 and Q3 are not on. Okay, so if I want to change this, let me change the value of this to lesser value. So let me say, I'll say change it to 330 ohms or 470 ohms, 470 ohms. Okay, and this also to 470 ohms. Okay, and this value is 470 ohms, and this value also to 470 ohms. Okay, and let me run this. Okay, if you see here, the DC motor is rotating in one direction. Okay, so this is as expected, and I'm getting a signal at P2.0 and P2.2. P2.0 maps to Q1 and P2.2 maps to Q4. Now if I want to change the direction of the motor, okay, at that time I need to assign 1 to this base and 1 to the base of Q3. Q2 and Q3 should be 1. So it will be 1 0 1 0, that is nothing but A, 0A. So let me stop this simulation. Let me go to key, and I'll say instead of 0 5, earlier it was rotating in a anti-clockwise direction. Now I will change the port pin values to 0 1 0 0 0 0 1 0 1 0. So this should make my motor rotate in a clockwise direction. So let me build the target. Okay, and now let me go here to the proteus and let me run. Now it should rotate in a clockwise direction. If you see here, it is rotating in a clockwise direction and as expected. Okay, so this is the demonstration of DC motor direction control using H bridge. Now if you want to achieve a speed control, then you have to use something called as PWM. We will not discuss that in this particular session. Okay, now let us talk about LCD interfacing with microcontroller 8051. Before we talk about the interfacing with the LCD, we need to understand how the LCD panel works. Now, if you see the below diagram, there are three different sections. One is SS, VDD and VEE. These are the power pins and intensity pins. RS, RW and E, these are the control pin. And then D0 to D7, these are the data pin. Now, whenever you want to write something or read from microcontroller, from the LCD panel, then they have to be written or read from the data pins. Okay, I repeat it. Whenever you want to write something or read something from the LCD panel, then you have to write it to the data pins or read it from data pins. Okay, so now let us explain about these control pins. Now if you see on the left hand side, there is a pin called as RS. RS, it basically stands for a select mode. So there are two different select mode. One is the command mode and another is the data mode. Now what is the difference between these two? So say for example, if you want to use a LCD panel, then there are some initializations that has to be done in the LCD panel, or specific instructions that have to be given to the LCD panel which are not the data. As an example, if you want to clear the LCD panel, or if you want to set the cursor at a particular location, or if you want to blink the cursor, or if you want to enable 2-line mode, or enable 4 data bit mode or 8 data bit mode. These are all the commands that are given to the LCD panel. Now, if the LCD panel has to be set in the command mode, then RS has to become low. Now, once the LCDs are initialized, then we have to send the data, and the data is sent or read from data pin D0 to D7. When we want to do that, then RS has to be set in data mode by asserting it to high. Okay. Now, when you are setting in a command mode or a data mode by either putting RS is equal to 1 or 0 or 1, at that time you may read from the LCD or you may write to an LCD. So what are the difference between when do you need a read operation and when do you need a write operation? Say if you want to clear the LCD, then LCD screen, then you have to put the LCD in the command mode, as well as you have to send or write some data in order to clear it. If you want to set the cursor in row 1 position, then you have to set the LCD in command mode as well as write some data. So when you are doing a write operation, at that time RW should be 0. Okay. So there are certain times when you want to read the LCD. So as an example, if you want to read the status of the LCD, that means if you are writing the data continuously to the LCD, and if you want to make sure that the LCD is not busy, then at that time you want to read the status of the LCD. So whenever you want to read the status of the LCD, at that time you have to put the RW to high. That is, you have to assert RW pin to high. Okay, and whenever you want to enable the LCD or latch the data in the LCD, then you have to use pin E. Now with that, let us go to what are the different commands. So if you see this particular table in this image, the bottom is the LCD image and the top right shows what are the different LCD pins that are available and what are they used for, and the left shows you what are the different commands that are available. So the one hex stands for clear display. Okay, and say for example, if you are using F, okay, that means you are setting the display on and cursor is blinking. Okay, and if you are setting it to C, then cursor is on, display is on, but cursor is off. Okay, and if you are setting it to setting the command to 80, that means the LCDs will be we will be pointing to the first line and first column in the LCD. If you are sending the command as C0, then we are pointing to the second line, first column of the LCD. Now, having said this, now let us see what are the operations that needs to be done in order to write to an LCD. The first and foremost thing is that it has to be set in a 2-row mode and 8-bit mode. Okay, so this is done by a command called as 38H. Okay, I repeat it, it is done by a command called as 38H. Now once you have done this, the initializations are as in the following sequence. First you have to clear the screen. Okay, in order to clear this, first you have to clear the screen. Before you clear the screen, you have to switch on the display with the cursor being blinking. That means first you switch on the display and let the cursor be in the blinking mode. That means you have to issue a command called as 0F. Okay, so So once you have set a set a command of 0f, then you will be clearing the display that is given by the command 01. Once you have cleared the display, you will increment the cursor position to one location to the right. So you will send a command called as 06. I'll reiterate. First you will send f, then you will send 1, and then you will send 6. Okay, all these things are sent in the command mode. Once you have sent these things, then you will force the cursor to some location of your interest. Okay, so let me repeat the sequence again. First you will switch on the display and put the cursor in the blinking mode. To do that, you will send 0f as a command to the LCD. Then after that, you will clear the display. In order to clear the display, you will send 01 to the LCD in the command mode. After that, you will send 06 and you will increment the cursor position to one location to the right hand side. So once you have sent all these three commands, then you will set the LCD to the position of interest. Say if you are interested in writing from 85 onwards, then you will send 85 as the command, so that the cursor will be pointing to 6th column of first line. If you are interested in writing to 4th column of second line, then you will send C3 as a command. Okay, so once you have sent these 4 commands, then onwards you will start sending the data one by one. Now whenever you send the command, you need to understand that you will be setting RS to 0, and then you will put the enable pin high and then pull it low. At that time, those data that you have sent as a command will be latched in the LCD module. Okay, so when you are sending the data, at that time you have to send RS as 1, then you have to send the data and enable the pin, that means assert the pin E6, okay, as high and then low. That will latch the data in the LCD module. So since we are writing this, then by default this data will be 0. That means RW pin, that is pin number 5, will always be 0. So with that explanation, let us go and write a program to send some message to the LCD panel, and then we will use Proteus to simulate and see what is the result that is being printed in the LCD panel. Okay, this circuit layout shows the connection between the 8051 and the LCD panel. The LCD panel that I have chosen is LM016L. So let us analyze these connections. Now port 2, they are all connected to the data port, with D0 connected to P2.0 and D7 connected to P2.7. Okay, so the data pins are all mapped to the port 2 pins. So if you want to write some data, whether it's a command related data or whether it's a data to be displayed, then you have to put those things in port 2. Okay, now if you see the voltage pin, okay, VSS is grounded and VDD and VEE is connected to 5 volts. Actually VEE is to be connected through the potentiometer. For convenience sake, I have connected it to 5 volts to get a maximum intensity. And RS pin is connected to 3.5 P3.5, RW pin is connected to P3.4 and E pin is connected to P3.3. So I'll repeat it. E pin is connected to P3.3, RW pin is connected to P3.4 and RS pin is connected to P3.5. So if you want to set the microcontroller in the command mode, then you have to meddle with RS pin so as given in the figure. Okay, so if you want to put in the command mode, then you have to set rs is equal to 0. If you want to set in the data mode, you have to set rs is equal to 1. So if you want to set it in the command mode, then p3.5 has to be low. If you want to set it in the data mode, then p3.5 should be high. Okay, so whenever you want to write, then since p3.4 is mapped to rw, so 3.4 should be set to 0 when you want to write, and 3.4 should be set to 1 when you want to read. And similarly, whenever you want to enable and lag the data, so first you have to set p3.3 to high, and then you have to set p3.3 to low in order to lag the data. I repeat it, rs pin, that is p3.5, should be low when you are in a command mode. Okay, the rs pin that is again connected to p3.5 should be high when you are in a data mode. Okay, and 3.4 should be low for writing operation, and p3.3 should be initially set to high and then low, so that we can lag the data. Okay, so for convenience sake, we will always put p3.4 to low, because we will not read the status from the from the LCD panel. Rather, we will work the LCD panel using some delay. Okay, now having explained about this connections, let us go back to the key. I have a delay routine that has already been written. I am not writing it just for the sake of convenience. Okay, now let me start writing the line one by one. Initially, I have to say start. I'll have to send 38h. Okay, so I say move a comma hash 38h. So this is to set the LCD panel to a 5:7 matrix display in 2-row mode. Okay, so once I send this is a command. I say a call cmd. Okay, then as I said earlier, we have to follow some sequence. Okay, the first sequence being, first you have to set the display on, then you have to clear the display. Okay, so we will send 0f first and then send it as a command. So we say move a comma hash 0fh, then a call cmd. Okay, then we say clear display. Clear display stands for 01, so we will send 01 to a h, then a call command. So far we are sending only the commands. One is to set in the 5:7 matrix mode, then display on and the cursor blinking, then clear the display. Then after setting the clear display, we have to shift increment the cursor position to the right. So that we do using 06. So we say move a comma hash 06h. Okay, hash 06h. Okay, then a call cmd. Okay, now once we have done that, we have to set the cursor position, whether it's in the line 1 or line 2, and the column position. 80 stands for first line column 1, so I'll set it at 85 so it will be going to line 1, and if it is 85, it is 6th column. So I'll say move a comma hash 06h, then 85h. Okay, then a call cmd. Then onwards I'll start sending the data. So initially I'll write high, so I'll say move a comma hash h capital, then a call. Now it is not a command, it is a data that we want to print. So I say disp. Okay, then I say hi, see move a comma hash I, then hash I, okay, then a call disp, then I will keep on looping. Okay, so what do I do here? Loop, loop, okay, I say a call jump, jump o. Okay, once I am done with the display, I will keep on looping there itself. Okay, so after this, what I am going to do is I am going to write the subroutine, say cmd, and then I will say writ from command and disp. Then for this I have to write. Okay, now so when during the command we have to remember that we have to set rs to 0. Okay, and then we will say rw to 0, and e will make it high and will make it low. Okay, but before that we have to put the data in which port, that we have to see it from the proteus. So we have to put the data in port P2. Okay, so with that in mind, so we'll say that for command we say move P2 comma A. Okay, and once we have moved the data, we have to set rs to 0. Now where is that rs map to? So we'll go to the proteus. rs is mapped to pin P3.5. so we say set CLR P3.5. so now we have set the LCD panel in command mode, then CLR P3.4, that means we have set it in a write mode, then set bit P3.3, okay, then CLR P3.3, then a call delay DLY. so whatever delay subroutine we have written, what is that delay? DELY, and then we have return. Okay, so similarly we will also do the same thing in the display mode. Okay, so in the display mode what we have to do is we have to move the data to P2, then we have to set the data the LCD panel to the data mode. That is done by setting rs to 1, rs maps to, let us go back, rs maps to pin 3.5. so we have to set the P3.5 to high, then P3.5 to high, then clear P3.4, that is RW will be equal to 0, that means it is a write. Then we will set the enable and uncheck the enable, and then we'll call delay. Okay, so that is the program that we have. So let us build the program and see if there is any error. Okay, there is no error. So let us go to the LCD panel. So we will select the LCD hex. Okay, and let us run this. Okay, so if you see here, the message hi is displayed. Okay, so that is about the first set of experiment in the LCD panel. Extending this particular program further, so what we will do is we will go back and say hello HE. So we will copy this and we'll say HELLO L O, then we will, what we will do is after displaying this, we will go to the next line. So the next line is we'll copy this. This is corresponding to the first line, so we have to go to the next line. So how do we do that? The second line starts with an address of C5, so C0, so we'll put it as 0 C5. Okay, and then we will give some other words here. Hello, like I'll put my name. Okay, R A J A N. Okay, so once I'm complete, so okay, this is also ASP. So let us see again. So here I have to call, whenever I pass C5, I have to call command, because aligning it, setting the line number 2, setting the cursor to the line number 2 position is a command. So this is fine. So let us see what was the program again. What it does, it will set it to 5 by 7, and then it will display, switch on the display, cursor blinking, and then clear the display, then advance the cursor, put it in the line number 1, display hello, put it in line number 2, display Rajan. Okay, so okay, then it will loop within itself. So let me compile this, and once it's compiled, there is an error, line number 32, DISP. Okay, once it has been compiled, so we will run the same in the proteus. Okay, so let me stop this execution, previous execution, and let me rerun it. This is hello RAJAN. Okay, good. So basically it has displayed hello in first line and then Rajan in the second line.